Alright, here I'd like to show you how with a patch of the plane, let's say, it could be any patch of any RN, but here in this example we're doing in 2 dimensions, so a patch in the plane, right, and a metric, okay, a metric matrix. You see this right here, this matrix, that's the metric matrix, which is really, notice, really a matrix at each point x, y, in this y plane here, at each point x, y, there'll be one of those matrices. Okay. Now, the one I have stated up there, it's x squared, x times y, on the lower row, x times y again, y squared, right? And separately, here on this side, I've listed the the components are, so g11 is x squared, g12 is x times y, g21 the same thing, and g22 is y squared. Notice again how this matrices, right? For example, g11 is really g11 at x, y. So they're functions of x and y. Okay, so basically, again, there's one matrix at each point x, y in the plane. All right. So now, look at that xy plane, but imagine you're not seeing any of those things that are drawn there, neither those two vectors or that disk, and instead you just see that curve right there. Turns out the graph of, or the parameterization of the curve, I should say, is this: gamma of t is t times t squared plus 1. Okay. So now we're going to ask several things. So first of all, we want, let's say, the length from a given parameter A to a given parameter B of that curve. How do we compute it? Okay, so what you got is we take the derivative gamma prime, which in this case is 1 comma 2t, and this is the length formula right here. So you take the integral from a to b of the length of gamma prime, and you integrate it. Now remember that length comes from the dot product, and you compute the dot product using that matrix that we showed you up there, and that matrix depends on the point. That's where we're taking the dot product at gamma of t. So that's what you have, square root of, and the square root is just, because for the length you take the square root of the dot product. Okay, so let's see if how are we going to do this. Well, first of all, here's the general formula for the dot product, right? The dot product of two vectors at a point is just going to be the summation over I and j of gij at the point times ui vj. Ui and vj are the ij components of the vectors u and v. In this case, we're going to use the same vector, so v is going to be the same thing as u in the case of because we're taking the length of a vector, in other words, the dot product with itself. But in general, if you needed two vectors, that's how you would do it. So here we are. So to take gamma prime dot gamma prime for that formula up there for the length of the curve, we just take g11 times gamma 1 prime plus g12 at gamma, I should say, gamma 1 prime gamma 2 prime plus g21 at gamma 2 prime gamma 1 prime plus g22 at gamma 2 prime gamma 2 prime. Alright, when we do that, here's what we get. Okay, remember that gamma of t was what? T comma t squared plus 1, right? Okay, so g11 at gamma of t is just the x coordinate of gamma of t, but squared, right? Because if you look at the matrix, let's go back up here. See, G11 is just x squared. Right, keep that in mind. And remember, G22 is going to be y squared. The middle term is just the x component times the y component. So here we have that we have then the x component squared of gamma, which is t squared, right, times the first component of gamma prime times again the first component of gamma prime as set by this over here, right there. So in the first component of gamma prime, since gamma prime turned out to be 1 comma 2t, it's just 1. Alright, now we just keep on following this formula up here. So we take gamma 1 2 at gamma, but remember that that's just, you get gamma, you get the x coordinate, which is t, and for G12 what you do is you multiply x times y, so you're going to get the x coordinate, which is t, and of gamma, and you multiply by the y coordinate of gamma, which is t squared plus 1. And that you're after that, so that there you have your G12 of gamma, and then you're going to multiply by gamma prime 1, which is 1, times gamma 2 prime, which is 2t. Alright. Again, the same thing for gamma 2 1, and the same thing for the other two components. They're just going to be reversed in order. Right? In the case when it's a vector with itself, they're always going to be reversed in order. And another thing is this, that it turns out that for the metrics that we want, they'll always be symmetric. So you'll always have that, for example, G21 will always be the same thing as G12. So it's not an accident here that, you know, you have x times y and x times y for G12 and G21. So those, you know, off diagonal terms are going to be like that. Alright, so we have that. Right, then we do a little bit of algebra. Simplify. We get up to here. Ooh. Finally, I get it to this level, and again, you can do more algebra and clean it up. You know, you're gonna have something, you know, with terms. See, terms even to the 6th power, t to the 6, and so on and so forth. I'll leave that to you. And that's it. And if you want to, you could do the integral. You know, pick the a and the b in this formula here. Pick the a and the b in this formula here. That integral from a to b, you know, to be fixed numbers if you want to, if you want a numerical answer. If not, leave them as a and b and just plug it in the integral, and you're going to get some expression in terms of a and b. Alright, so you got that. Next thing, we're going to do an exercise. So now you know how to get the arc length of curves. Now we're going to do an exercise just so that you get a feel for these things. So the exercise is this: what is the length of the vector 1 comma 2 with its tail at 1 comma 1? What do we do for that? Again, the first thing is take the dot product of the vector with itself at the point 1 comma 1. How do we do that? Well, you take G11, evaluate it at 1 comma 1, U1 plus U is the name of that vector. That vector 1 2 up there, calling it U. And U1 just means its first component, which in this case is 1, and U2, the second component happens to be 2 there. Alright. So anyhow, so for the dot product, you take G11 at 1 1. Remember that G is, you know, depends on what the base point is. And then, you know, you follow that formula there. So G12 U1 U2 plus G21 U2 U1 plus G22 U2 times U2. When you do it, you're gonna find this right here. Okay. G11 at 1 1 is going to be the first coordinate squared. Remember what the matrix was up there that I gave you? So it's just going to be 1 squared, because the x and y components of the point that we're basing on are just 1 comma 1. So x squared is just 1 squared times u1, which is 1, times u1, which is 1. Now G12 is going to be the x coordinate times the y coordinate of the point that we're basing on, but it's 1, so it just have what? 1 times 1, so it's going to be your G12, and you're going to multiply that by u1 times u2, which just happens to be 1 for one of them and 2 for the other. Same thing for G21 times u2 u1, you see it here. Right there. Okay, and you do the same thing with the last one. I put in the numbers for you, and that's what you get. And then if you multiply, multiply and add, you ought to get 1 plus 2 plus 2, which is 5, plus 4, which is 9. Alright, so that's the dot product of that vector with itself. If you took the dot product with the tail at 1 comma 1, and to get the length of the vector, we take the square root of that. So the dot product with itself at 1 comma 1 was 9, but then the actual length was 3. Now we'll do a second exercise. Let's say I want the same vector, that vector 1 comma 2, but now I want its length not at the base point 1 comma 1, but at the base point 1 comma 5. So what do? Again, we're going to use G11 at 1 comma 5, G12 at 1 comma 5, G21, G22 all at 1 comma 5, and then we're going to apply the formula for the length of the vector, which it was, let me see if I can move up to it here. The formula for that, for the length of the vector, was this right here, the u dot v formula. See that there? U dot v at p. Okay. Well, that's actually the one for the self dot product. For the length later on, not for the self dot product, just for the dot product, but you can take the self dot product and then you take the square root of that for the length. Okay, so let's go back to the exercise here. And here I've done for you the same thing as we just did before. Plug in, G11, U1, U1, G12, U1, U2, G21, U2, U1, and G22, U2, U2. And that's how we get that, 25 times 1 times 2 times 2, etc. Alright, and of course you add all that. You first multiply, then you add, and you simplify. You're going to get a number. You take the square root, and that's the length of the vector. Now, what did you learn from this? You find out that the same vector, what visually looks the same, and that's this picture that I had here in the beginning, those vectors that I told you to ignore, now consider them. So we had this in our picture. You see those two vectors? So we have the same looking two vectors, but yet when we take their length according to this thing, the length is different. So the vectors in themselves don't have length. What assigns them the length is the dot product. So now you have that even though they look to have the same length, the length was actually different. For the lower one, the length was 3, and for the upper one, the length is going to be whatever you do when you add up all those numbers in the second exercise and you take the square root. Okay, so now one last thing I want to cover, and is this. Up there I had before I had drawn like in the XY plane, I had drawn a disk. So now I want to consider one last thing you may want to do with these things, and the last thing is this, that given that disk, you may want to take you might want to figure out the area of that disk. Now, to figure out the area of that disk, right, according to this metric, what you do is the following. You take the integral over the disk, so you need to know from, Calc 2 or Calculus 3 how to take the integral over a disk, over a region of a function. And the function that you're going to take is the square root of the determinant of that metric. So what do? You get that metric matrix that again is really a function, of the points, and you take the determinant of that matrix, which is going to turn out to be x squared times y squared minus x times y, right? And then you're gonna get the square root of that, okay, and integrate it over the whole thing, over the disk, in others. Right, so that's the procedure that you normally do. Now, that matrix I gave you originally is pretty contrived. I mean, I just made it up. It didn't come from any standard or famous known geometry. So now we notice something here, that when you take the determinant of that, let's see if you get x squared times y squared minus that, which is x squared and y squared. So it seems like this thing has determinant 0. So perhaps that metric to begin with wasn't very good. But it doesn't matter, because what I wanted to show you is just the procedure that you do to compute. And all that is fine in this thing,